Welcome back. Good afternoon. Here's our final session of the asteroid observation portion of our program. Again, for people following us online, you can follow us on the chat session at the website www.nasa.gov/asteroidworkshop. Also follow us on hashtag #FindAsteroids. Kick off our next speaker is Jane Liu from MIT Lincoln Labs. She's going to be talking about laser radar for characterization and orbit determination of NEOs. Go ahead, Jane.
Oh.
Go ahead, Jane. Can you hear us?
Yes. Can you hear me?
Yes, you're coming through loud and clear. Go ahead, please.
NASA's Asteroid Grand Challenge. I can't see my slides, so you actually have to make sure that you guys see what I see.
Yeah, that's
The
fine.
slide shows the orbits of all the known potentially hazardous asteroids, numbering about 1,400 as of early this year. The near-Earth objects are discovered by optical telescopes, and the initial measurements establish the preliminary orbits. But when the optical astrometric arc is only days or weeks long, the orbit is so uncertain that we cannot predict whether the object is on a potentially hazardous.
You've lost your audio. Jane, can you hear us?
Yes, I can. Can you hear me?
Yeah, you're cutting in and out. Are you on a landline? Jane? Okay, I tell you what, Jane, we have some technical difficulty. We cannot hear you. I suggest we switch the order and we'll try and sort things out. We'll come back to you, Jane, if we can have Bijan present, and we'll try and sort out the audio issue with you, Jane, and we'll come back to you. But right now we're going to go to Bijan Namadi from the Jet Propulsion Laboratory. He's going to be speaking to us about measuring the size of NEAs with coherent Doppler lidar. So Jane, again, just we'll come back to you, Jane, once we get the technical audio issue resolved.
Okay, I will start. The focus of my talk is that class of asteroids that is a 10-meter class. These are H28 to 30 magnitude asteroids that are difficult to detect. And I think Jane was about to tell us that once they're detected, they're very hard to keep track of. Almost none of these multi-100,000 asteroids are known. And of the few that have been detected, almost none have been tracked again because the astrometry on these is too poor. So while I'll be talking about the characterization of these with coherent and actually incoherent lidar, the prior question is also important of how do we even find them, and if we find them, how do we know where to point to? And so those are all parts of this talk. And it turns out that the solution that we have is adaptable to a single large facility, but aspects of this solution are adaptable to multiple smaller facilities in the detection area. The other thing is that the technology that I'll be talking about is going to make it possible to observe these asteroids over sufficiently long times that we're going to be able to detect their acceleration and hence their mass and density. The facility, if it was one facility, it would look something like this. It would be a 4-meter class telescope that could be used to both transmit and receive basically signal, the laser signal. An example would be the 3.6 meter AFRL telescope. Our group is in collaboration with the USAF on an inverse synthetic aperture LiDAR project for imaging using a facility like this. And we've been working on this technology for about the last year. The telescope would be augmented with a laser system. The laser system would have a coherent laser that would be 1 kilowatt class, perhaps working at 2 microns, and it would be capable of imaging an asteroid of that size. It would have to have a chirp system that can chirp the frequency of the laser by as much as tens of gigahertz per second. In addition, because of the fact that the incoherent lasers are more readily available at higher power and relatively modest cost, one could augment this system with a like a 5 kilowatt, and I think maybe June will tell us about a 10 kilowatt laser, perhaps working at NIR, typically 1 micron, for range and size determination. Such a facility would need to have adaptive optics. The adaptive optics are necessary to get a diffraction limited transmitter, and you also need, in the coherent detection part, to match a local oscillator, the phase of the local oscillator, with the return from the target, as I'll be talking about in a moment. In addition to all this, you would need an acquisition, tracking, and astrometry system. This is similar to something that was mentioned earlier, a shift and stack, except that now the advent of the new cameras that have been available the past couple of years, such as the EMCCD, but particularly these scientific CMOS cameras that can have high frame rates and low read noise, makes a really kind of a revolutionary leap possible in acquisition, tracking, and astrometry of these smallest objects. In addition to that, you would need a graphic processing unit or some other high power computing. It turns out that the commercially available multi-$1,000 GPUs you can buy for science or for gaming can do fairly well this kind of work, and we've just done some experiments with that. I'll start the first part. Imagine the NEA is coming from a long distance away, 40 lunar distances, 1/10 of an AU away, and you actually have to detect it. Our shift and stack or shift and add technique, which we call synthetic tracking, that employs a high-speed, low-read noise camera, would be able to detect an asteroid that is of this class of size, and to be able to stack the images so that you have, for example, in this image at the bottom, you see two, let me see if I can use the laser. You see basically two images. This is a conventional long exposure image of a part of the sky that has an asteroid in it, a 19th magnitude asteroid, which makes this the typical streak. But a shift and add, what we call a synthetically tracked image, will pin that down to almost a resolution element for the telescope. In doing so, a dramatic difference will occur in the astrometry that's possible. We've demonstrated this year a 10-fold improvement of astrometry from approximately 80 milliarc seconds down to sub 7 milliarc seconds, and we think we could do better of this, and that would be sufficient then to keep track of this. Of course, that's relative differential astrometry. To get absolute astrometry, we would piggyback on, for example, a astrometric survey mission like Gaia, which is being launched from Europe by the Europeans next month. And Gaia, within a couple of years, will have everything brighter than 20th magnitude down to 100 microarc seconds, and would be fully capable of augmenting what we do with that. Okay, going to the laser range, basically, as the asteroid gets closer, and let's say it's at about 12 lunar distances, now a high power laser can be used, and the high power lasers right now are easier and cheaper to get in the incoherent mode. And if it's incoherent, then you would want to, our solution anyway, is to do an amplitude modulation of the laser. And you can operate in two modes. If you use a single amplitude modulated frequency, you can get the radial velocity. Once you know that, you can chirp the angular amplitude modulation to get the range and size. You would just look for a drop as you go from a long wavelengths to shorter wavelengths. You look for when suddenly the modulation level drops. And that's, I come from an interferometry background. We call that fringe visibility. And so when the visibility drops to a half, you've hit the top, you're now sensing the object size. Okay, that's the incoherent, but the title of my talk was coherent. So let's talk about coherent. This is also known as inverse synthetic aperture LiDAR, or LiDAR. It's also known as long-range imaging LiDAR, and it's basically the optical equivalent of synthetic aperture radar. And in this case, and it's also known as range and Doppler imaging, of course. And so in this case, what you do is you send a chirped laser beam with your telescope. The telescope basically narrows the beam down so that there's enough power on the target. You collect the return from the target, which now is extremely, extremely faint amount of light. But now with the coherent imaging, you can mix with a local oscillator. That can give you as much as easily 8 orders of magnitude of gain, so that you can now get a very good detectable signal. So that in this regime, we wouldn't need a quantum limited detector, whereas in incoherent we would. Okay, and so this can be analyzed, and from that we can determine the imaging. We've done some calculations on what we can do with such a system. Out to 40 lunar distances, we can detect a 10-meter NEO with a telescope like this in less than 2 minutes. LiDAR ranging, there's a table that shows you can go from 25% size error down to 1% size error at 2 lunar distances. So as it approaches closer and closer, you can image it better. And then in imaging, we find that we can get an SNR of 10 in each pixel of a 5 by 5 pixel image of this. And the final, and also the acceleration gives us mass, and I can go over that in the, if there's a question about that, but that's also available because synthetic tracking allows you to see it for so long. Over 5 weeks, there's enough motion that's astrometrically now visible, and now we can get the mass. Finally, this stuff is actually being put together in the lab, and so we are expecting to be able to report results soon.
Thank you. Right. Thank you, Bijan. Okay, any questions about this in the room? Okay. No questions? I did have one question, unless Pauline had one.
Well, my question is what's the time scale for this? How far in the future is this?
We have really had first light. We expect to have range Doppler images within a half a year. We should have full range Doppler in the lab at JPL. And this year, actually, in this fiscal year, our plan is to go out and do a field demonstration. And then with our partners at AFRL, we're hoping to actually go on their telescope and actually range an object in the sky. So.
Okay,
Good.
thank you.
All right, thank you very much.
Well, this is Lindley. You use the word detect. Don't you need to have an orbital, a pretty good orbit set to begin with?
Well, the idea would be to detect it for the first time. So you're scanning the sky, and the telescope has the sensitivity with synthetic tracking to actually observe it for the very first time. And when you observe it, then you can immediately start a regime of astrometry so that you can see it the next night, and on a logarithmic basis of time, you can detect it then within, a week later, you'll see it. And by the time you've seen it for over the 4 weeks that you could see such a thing, or 3 weeks, depending on the case, you have enough astrometry to see it at the next apparition. So you will never lose that again.
Okay, so you believe you can get enough of a return to actually do the initial detection?
Yeah. Yeah, we are experimenting right now with, we're almost at a photon limited regime in the lab, and we're going to try to demonstrate that this year to make sure that that's reality.
Okay, thank you very much. Appreciate it. If we can go back to Jane. Jane, can you hear us now?
Yes, I can. Can you hear me?
Yes, I can hear you. Sorry about the technical difficulties, if we could try your presentation again, and we'll begin when you are ready. Okay, go ahead, Jane.
So I'm on slide number 3, which says astrometric capability.
Yeah, we're with you.
So range measurement, before I was talking about how large orbit uncertainties mean that we most likely will...
Hey, Jane, we can't hear you. Can you try again?
Oh?
Yeah, can you...
Better?
Hello, can you try again?
Yeah, can you hear me?
Yes, I can hear you now. Please keep talking.
Are you on a speakerphone or something? You might have to go to a handset.
Hey, Jane, we can't hear you again. Can you try one more time? Okay. I think we're going to have to, Jane, we'll come back to you again. We're going to have to move on. So, Jane, just stand by again while we try and work out the difficulties. The next speaker is Stefan Kleen. He's going to talk to us about use of star trackers from existing satellite missions to measure light variation due to the rotation of asteroids. And when Stephen is ready, we'll begin.
Hello. Yes, it's Stephen Kleen here. I'm talking about existing high-resolution satellites. They have star trackers on them, and over half their mission, they have nothing to do. So I'm going to go over a few topics, give a little background on star trackers, a little feedback, too, description of operation. Yeah, advantages, and some recommended actions. Here's an example star tracker with a light shade. It has optics inside, CCD, and computation unit. So high-resolution Earth-observing satellites, like what take images that you see on Google Earth, need accurate attitude position. That's what they use the star trackers for. They precisely measure the position and magnitude of stars for input to the attitude control system. And there's a precedence for reusing star trackers for other missions. NASA's WIRE spacecraft did that, and they successfully measured stars, was their mission. Typical star tracker software can be changed on orbit after it's up there. We've done that, worked on systems. One challenge we have is the magnitude of what they're looking at. Currently, they're designed for a very fast update, and they do change what magnitude that they're looking at, and they adjust their hertz rate. So our challenge would be to going down to a low sample rate, a long exposure to get at magnitudes that we're looking for. But a little bit more on the operation. So the Earth-observing satellites are in a sun-synchronous orbit, and here's an orbit. And so half the time you're in the dark and you don't have anything to do. So it's a good time to look for asteroids. So the satellites and the operations are set up to respond rapidly. So you can change the uplink of what they're tasking 10 minutes before it comes into view. Typically, you do it like 2 hours before. So if asteroids comes in, you could get into it fairly quickly if it's within range for that spacecraft. And at this altitude, the spacecraft orbits every hour and a half, so you can get another access, and so you can get repeated access, or you can use multiple satellites and get continuous access, providing the moon or other things aren't in the way. So the operation would be to aim one of the star trackers at the potential asteroid and take the measurements. In addition to lengthening exposure time, we could look at image stacking, as was talked about on other presentations. The advantages of space, and people know this, you get rid of the variation due to the lower Earth atmosphere. Access time is pretty predictable because you don't have to worry about the clouds not being in the way. And if we use sensors that have been up there for a while, the star tracker sensors are very stabilized, and their characteristics are pretty well known. Also, this shouldn't impact the spacecraft's operation. The power budget, the star trackers are typically left on through the whole orbit. So the main mission here would be, once you find some asteroids, to measure the light curves, because you can do repeated measurements on those. It would be relatively low cost to some other things, because the asset's currently in space, and you're doing a cost share with the infrastructure because of the main mission as the ground station and personnel to maintain it, and the communication links. So one thing to do is take inventory of what star trackers are out there, determine the best candidates, come up with a test operation, using ground-based test units, upload the software. In addition to this tracking software, there could be some tasking software that would need to be upgraded on the ground system. And then you can test it with some fate objects until something comes into view. And with that, I can take questions.
Thank you.
Thank you very much. Okay. Any questions from in the room? Any, Lindley, anything? Oh, we did have one. Sorry. Go ahead.
When the satellite is on the back side of the Earth in the shadow, are there typically any activities going on that would keep you from using the star tracker? Meaning you can't turn it or move it, or the operator's engaged and so they couldn't process?
Yeah, for most of the satellites, that wouldn't be an issue. Sometimes we're doing downlinks, but typically the high gain antenna is a gimbaled antenna, and we do normal imaging and downlink at the same time, so you could do that.
Is aiming the star tracker expensive? I mean, is there a fuel cost or energy cost?
There's a little bit of energy cost of running the reaction wheels, but you're going to be running the reaction wheels anyway to keep yourself in so there is some, but it's relatively low. We've actually, we do some with the main telescope at night operations for calibration, but that we have to start watching the power budget.
One quick question on, well, field of view was one question. And part B is how far can you push the magnitudes? How faint can we go?
Okay, so field of view I can answer.
Yeah.
Typical range is 8 degrees, 8 by 8
Okay.
degrees. And how far that's the big challenge here.
Right.
So.
Do you have any kind of estimate on limiting magnitude? I mean, that was my question too.
Yeah, that's TBD.
TBD.
TBD. Okay. Thank you very
Thank you.
much. Thanks. Okay, we will try and go back to Jane.
Yep,
One more
I'm
time.
here.
All right.
Okay, sorry about that.
Third time lucky.
Okay, so I hope my slides are showing, and I'll just start with slide 3, where I'm addressing the problem of large orbit uncertainties. So range measurements can drastically reduce the uncertainty of an asteroid orbit. So this table on slide 3 shows the ability of different techniques to measure range and angle position. Radar can measure the range of a target very accurately, with about 10-meter accuracy. But due to its very large beam, radar is not very good at angle measurement. In contrast, traditional astrometry, which is passive optical measurement, is poor at measuring range, but is much better at locating the target's angular position with an accuracy about 1 arcsecond. But there is one third technique that combines the best of both radar and passive optical measurement, and that's laser radar. So next slide, laser radar versus radar. So as its name implies, laser radar combines radar and optical wavelengths. It involves sending a beam to the asteroid and detecting the reflected signal. But whereas radar uses radio wavelengths, laser radar's wavelength lies in the optical or the infrared. The first solar system object beyond Earth to be observed with laser radar was the Moon, and it was done back in 1962. But current laser radar technology is capable of going much further than the Moon. We believe we have enough laser power and good enough detectors to probe asteroids all the way from the near-Earth region all the way to the Jupiter region. Laser radar's advantage lies in its relatively short wavelength. Now remember that the diffraction limit of any telescope, whether sending or receiving light, is lambda over d, where lambda is a wavelength and d is a telescope diameter. For Arecibo, lambda is 12 centimeters. For laser radar, lambda is 1 micron. So that is 5 orders of magnitude smaller than radar's wavelength. A radar telescope, admittedly, is much larger than an optical telescope, but only about 1 order of magnitude, and that's not enough to make up for the wavelength ratio. So as a result, lambda over d is much smaller for laser radar, which means the laser beam diffracts much more slowly than the radar beam. And since the laser beam diffracts more slowly, is relatively small when it reaches the asteroid, and thus produces much more intense beam on the target. So depending on the size of the asteroid, the laser beam can be even smaller than the asteroid itself, in which case the entire laser beam is intercepted and reflected by the asteroid with no wasted power, as indicated by the drawing on the lower right. So in this situation, the laser radar signal scales as 1 over r squared, where r is the distance to the asteroid. In contrast, if you look on the left drawing, the radar signal-to-noise always scales 1 over r to the 4th, and that is why radar can only observe asteroids that come really close. So next slide. The laser radar system we envision includes 2 large telescopes in the 10-meter class, one to transmit and one to receive the laser beam. The transmit telescope needs adaptive optics because we want the transmit beam to be as close to diffraction limited as possible in order to maximize the power on the asteroid. The requirement of the receive telescope is much less stringent. Its job is simply to be a photon bucket, just count the number of return photons. And since there's no imaging involved, the receiving telescope can just be one big telescope or a bunch of smaller telescopes. The laser would be a 20 kilowatt ytterbium-based cryogenic laser. Material properties like thermal conductivity and refractive index are much better at low temperature, so cryogenic lasers can produce high power efficiently with near ideal beam quality. The spectral line width of such a laser is also very narrow, allowing the use of very narrow band filter to minimize background light. Cryogenic laser technology is well established, and 20 kilowatts is well within the capability of current technology. For the detector, we would use a type of low noise photon counters called superconducting nanowires, which are cryogenically cooled below 4 Kelvin. These detectors have high quantum efficiency and very low dark counts. All the main components of this system, the cryogenic laser, the superconducting nanowires, and adaptive optics, are areas of expertise here at Lincoln Lab, so we're confident that we can build these components. Next slide. Now this slide should say laser radar capability near Earth region. This plot shows the expected performance of a laser radar system compared to Arecibo and Goldstone. So the blue line, the blue curve is laser radar, the red curve is Arecibo, and the green curve is Goldstone. The y-axis is the geocentric distance in AU, and the x-axis is the diameter of the asteroid in meter. So this plot answers the question, how far out can an asteroid be detected at a signal-to-noise ratio of 3? And the assumptions are stated at the top of the slide. So the plot shows that if you look at the 1 kilometer size, that laser radar can see a 1 kilometer object as far out as about 0.7 AU, about a factor of 2 further than Arecibo. The drawing to the right of the plot illustrates what laser radar can do. So it shows an entire asteroid illuminated by the laser beam. So photons coming back will have different arrival times because they're reflected from different parts of the asteroid. The photons hitting the front edge will come back earlier than the photons hitting the back edge. So the photon arrival times not only tell us how far away the asteroid is, but also something about the asteroid shape. And as the asteroid rotates, we can probe its other dimensions. The resolution of these shape measurements depends on the signal-to-noise, and in theory can be as good as 20 meters. And this kind of resolution can be matched only by radar and space missions. But laser radar can reach many more objects than both of those techniques. And finally, combining the science information with the range, we can calculate the asteroid albedo, which tells us something about its surface composition. Okay, next slide. Now, this should say probing inner solar system with laser radar. So this plot is similar to the plot you saw on the earlier slide, but now the y-axis extends all the way up to 6 AU, and the asteroid side range is now 1 kilometer to 100 kilometer on the x-axis. So we can see that laser radar can observe a 10-kilometer object as far out as the main asteroid belt. 100-kilometer size objects can be seen even beyond Jupiter's distance. So this includes large Trojan asteroids as well as several of Jupiter's regular satellites. Okay, so next slide. Here I'll just summarize the benefits of a dedicated laser radar system. A dedicated laser radar system can guarantee the recovery of newly discovered objects, which would be a welcome help to Arecibo and Goldstone, who are already heavily oversubscribed. Laser radar's main benefit is its sensitivity to a wide range of asteroid sizes over a large distance range. It can yield range, size, optical albedo. And this table shows the cost of a full capability prototype to be used on existing telescopes. And it lists the cost of the main components, right? The laser, the detector, the adaptive optics. And so the total cost is on the order of $24 million spread out about over 3 years.
Jane, you have 1 minute, please.
Yep. So in summary, laser radar technology is advanced enough to probe essentially the entire inner solar system. A dedicated laser radar system basically opens up a brand new way to look at solar system objects. It can refine orbits for impact forecasting, space missions, and it can provide shape information, size, and surface composition for a wide range of objects. And the technology already exists. It just remains to be put together. And that's it. Thank you.
Thank you very much.
Thank you.
Kenny, any comments and questions in the room? We have one.
The chart that you put just before the summary talked about with the existing telescope. This again is a 10-meter class telescope.
Yes, it is. I'm referring to you. I'm referring to existing 10-meter telescope like the KEX.
Okay. Any other questions in the room? We have one more.
Real stupid one. Can we can aim a laser beam at an asteroid in the main asteroid belt and actually hit it?
So the question is, can we aim a laser beam at an asteroid in the main belt
and
hit it?
That's amazing. We can do that. I just think it's cool.
I believe we can because, and even though the laser beam is much smaller than the radar beam, but it depends on the asteroid size. If the asteroid size is smaller than the laser beam, it should be no problem at all.
Wow.
Okay. All right. Thank you. I think do we have another one? One in the back. Last question.
Hi, Jane. Is it possible to make the laser beam broader? Because you were saying it's a 6-kilometer diameter laser beam at 0.1 AU, and there's very few near-Earth asteroids that we have positions as well as 6 kilometers. So would there be a way to, say, broaden the beam to a couple hundred kilometers to initially find it and then home in once you found it?
Sure, it's easy to make a beam broad. You just don't, it's limited. Without adaptive optics, it's a seeing that limits the size of the beam. If you want a broad beam, just take away adaptive optics. But then you really decrease the intensity on the asteroid. So
It's just
typically
there's so few near-Earth asteroids that we have their positions down to 6 kilometers. In fact,
I see.
I think there may only be one.
Right. So yes, we can do that. So we can spread out the beam to locate the object, and then turn on the adaptive optics once you have a good position for it.
Okay.
All right. Thank you. I think we have to move on to the next talk. The next talk is by Chris Lewicki for Planetary Resources, leveraging Planetary Resources network of ARCID 100 space telescopes to be launched in 2015.
Afternoon, everyone. Happy to be here today working with NASA and the Asteroid Initiative and looking at all the options for exploring the asteroids. We're particularly interested in those activities which we might work together on creating infrastructure and especially identifying and characterizing asteroids which may be of potential future resource use, whether that resources are for future human use in NASA exploration missions or even commercial missions. So to summarize really my comments up front, Planetary Resources is working on ultra low cost, really off-the-shelf derived capability to go out and explore and characterize and identify the resources on asteroids. And in 2015, we'll begin with a demonstration of a prototype of that capability in low Earth orbit. And that affords some opportunities to use that platform and actually a network of spacecraft to perform, while we're up there, some asteroid characterization observations. There are things that we'll be doing both from a technology standpoint, which have nothing to do with the observation, and then while we are up there with an optic and a sensor, we can of course use that sensor to be part of the network of all the different resources that we have that can increase the global knowledge of NEOs. So this is part of a program, and it's not a single mission, it's an evolution of missions, and the goal is to create a capability that is commercially viable to go out and prospect and understand as many near-Earth objects as we possibly can. We've just been to 2 so far. By the end of the decade, we'll be to 4. If we go through with ARM, that will be 5, and that's a good start. But from a commercial standpoint, we're going to have to do much, much more. So we're looking at a program where we actually culminate in the swarm exploration of multiple near-Earth asteroids, and ways, as we're getting to that, where we can essentially risk reduce and demonstrate that capability in places like low Earth orbit. The focal point of that in the near term with an instrument capability is what we call the ARCID 100. It's our first instrument in space. This is the size of the spacecraft and the class of spacecraft that we would like to get out to a near-Earth asteroid. Once you take off all the propulsion and everything that you need to inject it into an orbit, you end up, if you're using secondary launches, with only about 15 kilograms of payload. And that is a fairly tiny package, and as a result of that, we want to put as much glass and as much optic as possible. So we have a 20 centimeter RC optic with a resolving capability of about an arc second, and through stabilization and other techniques, we can get down to sensitivities of about Vmag 19. And really just a broad range using an industrial CCD of doing imaging and photometric measurements, and using filters, we can get spectral characteristics to help bin things and either bring things into consideration or rule things out of consideration. And on the bottom there, you can see a full-size configuration prototype with me for reference on about how large these objects are. So we're putting a couple of these into orbit starting in 2015. There are, of course, a number of advantages for having things in space here, up above weather, up above the atmosphere. You effectively have a larger optic because of those advantages. Also, you have the advantages not just because we have a small constellation of a few of these, but the dwell time that you can have on target can be longer. Your ability to respond to a wider range of spots in the sky is possible. And really what I see with the ARCID 100 as playing a niche role of being able to do very rapid follow-up with things that are found by much larger scopes, being able to spend the time to get photometric study of them, to get light curves, and then where possible get even better than that and start to characterize these things by their resource potential. If I get the opportunity to speak tomorrow, I'll give a quick plug for it today. Part of the thing that we're going to use for these test beds in space is essentially data mining and algorithms. And we've started a project with Zooniverse, partnered with the Catalina Sky Survey, and with the great support of Tim Spar at the Minor Planet Center and lots of advice from NASA, of essentially crowdsourcing the ability and seeing how good our algorithms are, and then also working with NASA and turning those into algorithm competitions. And the whole idea behind this for planetary resources interests are a rising tide lifts all boats. The more objects that we can find, the better for everyone. The better we can characterize these objects in space, the better it makes our resource targets. And if we can put these algorithms actually on the spacecraft, which we would like to do with the ARCID 100, we can eliminate or greatly reduce our dependence on the data pipeline between here and Earth, giving us the option of putting those spacecraft out at distant points from Earth, out at the Lagrange points. So if we get the opportunity to present tomorrow, you'll hear more about that then. We're starting next year with a demonstration of hardware in orbit, and from software and technology and imaging stuff, we'll test out some of this on essentially taking the back end of the ARCID 100, which is the avionics section, and cramming all that stuff into a 3U CubeSat and deploying it via NanoRack service from the International Space Station through a crew resupply mission. And on this mission, we'll have the opportunity essentially to test out all these commercial and really low-cost approaches that allow us to consider asteroid rendezvous missions that can be measured in the millions, as much as maybe only $10 million for going out and doing asteroid rendezvous missions, and admittedly higher at risk, but essentially pushing the envelope forward and making this a commercially viable proposition. So to close on things and looking at, in terms of private-public partnerships and NASA leveraging things that are happening at Planetary Resources, we see low Earth orbit as really a proving grounds and a testing grounds of testing out technology, and the ability to have that as part of the portfolio, to be able to deploy instruments to test technology, to have things where we can do space-based sensing, get access to broader ranges of spectrum, and have this be part of the overall monitoring network. I think this is something that can help very much with the identification of targets and bringing those orbit condition codes down for all the very uncertain orbital parameters of asteroids that are out there. So for data that we produce for ourselves, data that we produce for the public through programs that we've started through our ARCID Kickstarter campaign, and data that we may produce for the government or scientific customers, there's opportunities essentially to create purpose-built observations where we can go out and get very specific types of observations that we can enable in a very rapid turnaround. These are types of things where secondary launches are available several times a year, and the ability to put up a new instrument, to pose a new observation, and get that into space is something that can be measured in certainly less than 2 years to be able to turn these things around. So whether it's dedicated Explorers class missions or leveraging the spare time on what we'll be doing for commercial observations, I think there's lots of opportunity there. The last thing I'd like to say is there is a lot of unused capacity that's going into space in the form of ballast or unused rideshare opportunities. And Planetary Resources is very interested in all opportunities that are going to space, especially those that are going Earth escape. And to be able to take one of these scopes and put it on a trajectory that is leaving the Earth, wherever that might be, is something that we would certainly be interested in working with NASA or whomever and taking advantage of those opportunities and not letting any launch opportunity go unused. Thank you very much.
Okay, we have time for some questions. Is there any in the room?
Yes, for this network, how many of these 6U telescopes do you need to cover the majority of the sky? And again, the magnitude question, how far can you go?
Yeah, so our objective isn't to cover a majority of the sky. We're putting up 3 telescopes, the first going in 2015, the next one's probably following, and a pair of launches in 2016. And for us, the goal is actually to start prototyping our swarm exploration strategy at a near-Earth asteroid. So because they are secondary launches, they may or may not end up being in complementary planes. But it's the type of thing in terms of being able to see a portion of the sky and have a revisit time on that that's measured in 45 minutes. So if you have a monsoon, or if you have bad weather, or if you're in the middle of a lunation, these are types of things where, while the rest of the planet is mooned out, so to speak, we have 2 or 3 days where we can essentially be one of the things that will still be able to operate while that's taking place. And as I said in the presentation, we're bound to about 19th magnitude with typical integrations on what you do with a cadence of observation anywhere between 10 and 20-second integration times.
Okay. Any other questions from the room? Okay. If not, let's move on. Thank you. The next speaker comes to us virtually. This is David Rabanis from Space Apps Chile. This is a CubeSat swarm with IR sensors and onboard data processing. So David, whenever you're ready, go ahead.
Yes, thank you very much. We are very grateful that we have that our proposal has been selected for this presentation at the NASA Asteroid Observation Session. We started out earlier this year in April in the Space Apps Challenge that was called by NASA. We participated in Chile, and our team, Carlos, Rodolfo, Eric, Anton, and myself, David, we have participated in this, and we tackled asteroid hunting. And we found, do I switch myself to page 2? Do you see that? Okay, so we tackled the challenge, which was to develop a mission concept for exploration of Apophis. That's one of the asteroids that is supposed to be having a close encounter in 2029. And given the damage that asteroids can produce, we thought it would be much more sensible to think of the many more that need to be actually tracked and observed. So I switched to page 3. Tagging and tracking only of one asteroid in this challenge was really not so much of a meaningful thing if there are more than 100,000 unknown objects that potentially can as well pose a risk. So we thought we focus more on how to predict the forces that act on an asteroid. That means we have to track the environment around them. And this environment around them means all the little masses that pull and tug on them. And that means we have to have a very complete picture of the asteroid belt. So basically, this is what we then tried to do in this challenge. And we wanted to propose a mission concept to map entirely down to a certain, to be decided size, the asteroid belt. Page 4. So we think we should do this in three phases. In general, it's a public learning project. Ground-based technology testing, of course, needs to be done first. That's one of the first phases. The second is massivation of ground-based hardware and operations. That means actually to put it on many more shoulders, crowdsourcing technology, and also bringing many more people into the game. This is also being presented in some other talks. I think tomorrow in the citizen science part. And then, of course, as our outcome from our Asteroid Space Apps Challenge mission concept was a concept for space-based systems that would be a swarm of CubeSats, potentially at the L2 Lagrange 2 point of Mars, to be closer to the asteroid belt, to have better signal. Next page. So the first phase would be ground-based technology testing. Here I have shown a near-infrared to thermal infrared transmission plot, and there's 4 prime frequency or wavelength ranges that I would like to observe with a telescope, and that allows us to discern the surface temperature of a asteroid or a planet from the background stars. So that would be actually basically probing this black body or gray body spectrum of the object, which is more significant than the optical reflection of these objects. So basically we need accessibility of this technology to amateurs. That means infrared sensors in that wavelength range, moderately cooled thermal infrared sensors, narrowband filters, and robotic telescopes. I switch to page 6. The phase 2 would be the massivation of this hardware. And that needs to be done by crowd-funded campaigns to, by the bulk, purchase infrared sensors, narrowband filters, cooling technology, telescope motion control, which is actually already pretty much available, but not accessible enough for my taste. Open source control software exists already, and so on. So we need basically involve the amateur communities in this. And of course, outreach campaigns at schools and colleges and so on are part of it. And especially in Chile, the Atacama provides a very good place to do it from the ground because it's very dry. So these transmissions in the infrared are very good. So we have very little losses in the atmosphere. And then, of course, we need to develop the image stacking and feature detection routines, which in optical astronomy already exist. Maybe they just have to be ported. And as a second step, as one of the last steps in this phase, there would be technology refinement for nanosats. That means miniaturization. And my personal wish would be to extend this infrared range up to 18 microns, which is a little bit of a challenge, of course. Phase 3 would then be to go for space-based observations. That means launch and operate a prototype in low Earth orbit, and later on designing the swarm that goes to the Lagrange orbit. And we would like to hitch a ride to Mars as one of the ballast loads that has been announced by NASA as well. My predecessor in this talk also mentioned it, which is a very nice opportunity to get far away from Earth. And we think of a swarm of 6 to 10 copies, maybe 12 or so. That minimizes the risk. And it would have to, we would need to have miniaturized ion thrusters to propulse us to L2, power, of course, from solar panels and so on. So many of these technologies are already in the process of being developed, and we personally would like to just focus on the new payload, which is this infrared various narrowband detection schemes. And we would like to engage radio amateur community for data downlinks, which also is a necessity to get the data. The flight configuration would be like in this picture, page 8, basically a telescope, which is a round telescope, deployable, obviously, from this CubeSat, pointing towards the main asteroid belt, and the other side pointing to the sun. That would be the normal flight configuration. The scanning would be a rotating spiral on the ecliptic plane, so every image frame would be reobserved various times. That allows us to stack the images and decrease the noise, and we just let time work for us and reobserve patterns on sky to reduce the noise. Basically, that's the idea. And with this whole challenge, we would actually have some synergies with other space challenges that have been formulated by NASA. That is the database for near-Earth objects, CubeSats for asteroid exploration, ArduSat, Height to Mars, and Why We Explore. These are the main themes that have connections with this, what we want to do. Thank you very much.
Thank you. Okay, any questions from anyone in the room? This paper? Okay. We have one question, David.
David, what is the focus on 18 micrometers? Why specifically that band?
18 micrometers allows you to have a highest possible signal if you have an object that has only 100 kelvins of surface temperature, so 120 or so. It's the peak radiation of the blackbody curve. So it allows you to probe the whole temperature range better.
Do you know the answer?
I don't think it is a necessity, but I think it's a good frequency or wavelength that allows you to really probe cold objects in our solar system.
Do we have time? One more quick question: Why are we observing the asteroid belt from Mars? Would it be possible to do this from the Earth L2 point?
It would be possible from the Earth as well, but we think that since we have only a CubeSat and only maybe a 20 centimeter size telescope, we would like to go to the site beyond Mars because we are halfway to the asteroid belt. That means we halve the distance, so we have 4 times more of a signal. So we can probe more complete the smaller objects. Or as a compromise, we don't need the very high top-notch sensitivities of detectors that are available today. So you know, it's a compromise, of course. Okay. But I think getting closer to the belt always gives you the square of the distance in gain in signal that relaxes your requirements on the sensitivity of the detector, which is actually the most benefit I can see.
Good. Thank you. All right, thank you very much. Move on to the next and last presentation of the session. This is Rick Tumlinson from Deep Space Industries. He's going to be talking to us about scouting missions that are required to characterize potential asteroid targets.
Hi there, my name is Rick. I am not a scientist or an engineer, although they let me hang around. I am going to be presenting for the company. I am speaking for the folks in the company, unless the things I say sound stupid, in which case it's probably coming from me, not Dr. John Lewis or Dr. Mark Saunter or many of the others who are involved in our company. There are probably about 20 of us right now in the company. This is the original plan, asteroid redirection. This is the way we would love it all to be. Big asteroid, lots of things going on, getting out there. This is where we are right now. I don't think this one's going to happen either. When it gets wrapped up, I call it the Jiffy Pop mission. I think it's important. I think these are great ideas. I just don't necessarily think that's the way we're going to go, sending out a very large and expensive mission to grab a small rock. Now, we went down the same path in our company, which was a small mission to grab a small rock, and we began to investigate what was involved with that, and we began to change our plans. And we are finding a lot more near Earth objects out there, and it's getting very, very interesting. Unfortunately, we don't know a lot about them. We can do a lot, as you've heard early in the session, as far as ground-based observation, et cetera, to learn what they are. But basically, you know, when you get out to the smaller sizes, you really don't know a lot about what's going on with them. We don't know whether they're solid, whether they're gravel piles, et cetera, and all of this begins to make a lot of difference, especially when you get out there. I don't know how many of you are familiar with the movie Spinal Tap, but in that movie, they had planned on a gigantic model of Stonehenge coming to their stage. It was supposed to be 18 feet high. Of course, they didn't do a lot of pre-planning, so what actually showed up on the stage was 18 inches high. It can be rather embarrassing if we send our astronauts out to something that we haven't really checked out in detail before we get there. So we need to find out what they are. Are they solid? Are they not solid? Now, we have a lot of opportunities to do so. We actually see some very interesting periods where we can get into some scouting missions and get out there in advance and start finding out what they are made of before we start mounting very expensive missions. These are various periods where we could actually send out small scouts to do different sorts of scouting missions. There are different kinds of scouting missions, which are basically visual, involving flybys. There's rendezvous, where you actually loiter and, in a sense, orbit around the actual object, and then you can actually get to the sample return. We have different classes of vehicles that we're looking at in our company that are being designed and missions are being laid out for. There are the Fireflies, which are flyby missions. They're fast, they're low cost, they're fast to target, they're repeatable. We have the Firefly, the Gnats, which is something that keeps flying around your head. Basically, it's a rendezvous mission which would loiter long-term around an object. There's the motherships, which we'll talk about in a moment, and then there's sample return, which are dragonflies. Firefly Scouts, small, 6 to 12U. We build them in threes. That's how we reduce our risk. Fly them on different vehicles. We believe we could build and fly 3 of these for under $20 million and probably have them in the air, so to speak, within 2 years of funding. Dragonflies, 10 to 50 kilogram sample return. Everything we do in our company, we do in threes. That is our clever risk reduction method. And you don't fly the second and third ones until the first one has made it through your most high-risk period of flight. We believe we could do 10 kilogram Dragonfly asteroid missions for under $50 million. Then there's the mothership carrier, which is being unveiled right now here for the first time. And this is one that gets into sort of the grand challenge. The idea here is to carry a large number of small 3, 6, 12U CubeSats or a large swarm of small ChipSats into space. Now, we have to do this in a new way. I'm using the term the new NEO initiative. Whatever comes out of what it is that's being worked on now is going to be something that's better than what we had. And that's what I'm excited about. We want to be able to deliver space science, industrial science, and planetary defense knowledge. We believe that we have to create the infrastructure and leave the infrastructure behind so that we can get out there and start doing things with the things that we discover. Remember, there's the threat and the promise. We believe that the models that work and are working today in LEO are the COTS model and then the ILDD model, which is being used with the Google Lunar X Prize. The COTS model is working today. There was a commercial launch of a SpaceX vehicle which carried a commercial vehicle into space, which was derived from a partnership with NASA and the US government to develop that vehicle. At the same time, there's another vehicle that docked with or burst with the space station and delivered goods to the government employees in the government space facility at a very much reduced cost that will begin to develop an Earth to LEO infrastructure that can be used for all for the benefit of all. We need to have a new relationship. Actually, somebody reminded me this is actually the old relationship, the NACA relationship, which predates NASA, relationship to the aerospace industry beyond LEO. The agency, we would like to see specify the needs, provide the tech development support, purchase data and information, and the private sector can develop the technology, operate the projects, and deliver that data information to the scientists who need it and want to get more of it. We believe that as a government, as governments of the world, as the people of the world, there are missions that are at that level. Mars, going to the moon, Phobos, Deimos, interesting asteroids on the way to Mars. That's where we want to see NASA go. That's where we want to see our government go. That's where we want to see the big, grand things happen. On the way there, we want to be doing our plans, which is filling up what we call free space with lots of neat things going on, including expanding the community of human life. Now, if we don't do it right, this is where we're going to end up. We know we are dealing with a dysfunctional body, and it's probably more risky to the human race than some of the things coming at us from space. Luckily, they can't pull it together, as we're going to hear about later on probably today. But this is what's out there. This is what we're going to have to deal with if we don't do what we're doing at this meeting the right way. But I believe if we as a community can unite and do these things the right way and operate in a way where we raise all boats and everybody gets what they need and works in a way that is cooperative and aimed at the goals that we all share, and we do all share the same goals, we can achieve amazing and magnificent things. Thank you.
All right, thank you. Okay, any questions?
We have one in the back.
Yep. Okay.
Hey, Rick. So, what's going to be the price of each scouting mission? What's going to be the price of each scouting mission?
Of each scouting mission, well, we believe that we can send the flybys, which are the Fireflies, the small ones, for around 20 million. And we believe we can do the sample return for about 50 million.
And apart from being a lot cooler to fly to an asteroid for a flyby, what can't be done from the ground, observation-wise?
You can't touch them. You can't touch them. You can't physically interact with them. I mean, it's important that we be able to look at these objects, but the actual, for example, the porosity of the object, the actual makeup, the physical makeup. Is this a gravel pile? Is it a tightly held, cohesive gravel pile? Is it a loose gravel pile? What occurs 1 meter under the surface? What kind of what is the compositional difference between the surface and its depths within the asteroid? These are things that you have to get out there and poke around and get involved with the asteroid to find out. And if you want to know more, I would suggest you talk to Dr. Morrison up here, who's the man. So.
Okay,
thanks.
Other than John Lewis, who's the other man.
Okay. Any other questions?
Follow up on that question. You say a Firefly mission is 20. That's 20 million for your first 3. What's the recurring cost if you want to send another 3?
I can't get into a lot of it. There is a very interesting profit built into that, and that includes the drop-in cost as we begin to get from the first down to the second and third. They actually drop down, and then we hit production lines. We can talk afterwards. We're a company. Just like my friend Chris, we're a company. We can talk afterwards.
Okay, any other questions? Any questions online? Okay, thank you very much.
Thank you.
All right, so now we have a little bit of discussion and synthesis. Lindley, are you still online?
Yeah, I'm still here, but I'm going to have to take about 10 minutes. You could go ahead and start addressing the list of questions that Pedro has come up with, and I'll be back with you in about 10.
Okay, so when you come back, just let us know, and then we'll go from there. If
Okay.
could one of the Pedro, do you want to just read the questions?
We
Or
have one.
you have them? Oh, we have them.
Here.
Okay, so
And these are directed to some of the presenters. Is that correct? So if the presenters are still in the audience, they could help us answer these.
yeah. So we'll go through these just one at a time. Okay, so this is from Ustreamer 911932 to Ray Pickard. What is the ROM cost? Number 1, and number 2, can you reach 10 microns like NeoCam? Is Ray? He's not on. Ray, are you online? Okay.
Okay.
So we'll save that one for later. For Gary Matthews, number 1, how good is the astrometry from USSS? And number 2, what is the magnitude limit?
The first part of the question from USS. What?
Yeah, it's a USSS. How good is the astrometry? Is the question.
That would let's see. That would probably
Space
depend on
surveillance.
the pointing. So that would be done by the spacecraft. So I don't know. And then I haven't looked at the at how far magnitude you could go down, but you know, at 1.1 meters, you know, should be able to go pretty far at 5 microns. So.
Okay.
So not very, you know, probably not a very pleasing answer. So.
Okay.
And there's a question at the back.
Yeah, let's we'll alternate, and let me go through this because this one person had several questions for several speakers. So we'll go through these. We'll alternate. We'll go through the room and come back and forth. This is for same questioner for Bijan this time. Bijan, does the LiDAR need pre-discovered objects or can it survey? That's number 1. And how many per year come within 0.4 lunar distances? Or 40 lunar distances. I think there's a typo there.
Okay.
04
Is this
LD.
on? Okay. I can certainly answer the first one. The LiDAR is not a great way to detect them for the first time. What you want to do is know where to point, and that question got raised before as well. And that's why the synthetic tracking is you know what we recommend to do, which is to use a passive detection system, and that will very efficiently find them, and it will also do enough astrometry so that you can point properly. Like if you have a 4-meter telescope with a 2-micron laser, that's a 100 milliarc second beam. You want to point to about 1/5 of that lambda over d, so to about 20 milliarc seconds. So if you had like 10 milliarc second class pointing, astrometry, you're in good shape, and synthetic tracking can do that. So LiDAR is great for ranging and sizing and imaging, laser radar, but for detection, you really want to know where you're pointing first.
Right. Okay. And then this is for Stefan Kleen. What magnitude limit can these star trackers reach? I think this was asked. And how many objects per year are bright enough to detect? Is Stefan still in the room?
Yeah. And yes, I don't have the answers to that.
Okay. Okay. And then we'll, if we can go to in the room at the top. Sorry, can you get that back in?
A lot of the presentations that we had seem to map one across the other, either technologies that connect or that could mesh together for solutions. Have they been mapped in any way? Has there been some sort of representation of where they plot together, or not yet?
Sorry, can you repeat that? In terms of mapping, in terms of the organization of the, or have they actually been mapped? Is that what you're saying?
Yeah, I think maybe the terminology is misleading, mapping or not. I guess the question is, these technologies seem to kind of connect together. They might actually kind of come together in terms of a bigger solution set. Has that worked of kind of analyzing how they might fit together or visualizing how they might fit together been done?
Not yet. I mean, that's one of the things that we're working on. If you notice the way we tried to structure the talks, they were trying to group in topic areas.
Absolutely.
So it was a good observation on your part. That's part of the process that we'll do right now.
Right.
Is after hearing the talks, hearing some of the presentations, go back and have a talk, and then we'll take that next step. Let's go to Paul. Why don't you read the next one, and I will pick out next speakers in the room. So question online.
From Nick Howe's Fox Telescope for Clinton Clark. Is he here? Yes. The question is, have you investigated the possibility of doing starfield subtraction for a crowded starfield, taking a known reference starfield frame and then using subtractive methods to identify moving objects?
Short answer is yes. And so there's pros and cons to that approach versus our approach. We probably don't want to go into here, but the short answer is yes. We've looked at it.
Okay.
Our approach is near optimal, which again, too much to get into what that means in terms of physics, but we've looked at it.
Okay. All right, very good.
Okay, questions in the room? Let's go this one, Chris.
Chris.
Right here.
So I think Lindley mentioned this at the intro that there was a population of people who are not represented in today's session, and those are all the professionals who are currently doing the work, all the different surveys, whether they're ground-based or space-based. And over the last 10 years, that has been progressing towards larger pieces of glass and more professionals as the task gets more and more difficult. This is just an open question. Is the objective in find all asteroids and those that may pose threats to Earth and know what to do about them? There's a mindset that could go in creating the single best way to do that, or trying to find the absolute lowest cost, broadest way to do that. And what do you think it is that will try to be optimized in that? And is NASA looking for the solution which kind of leverages stuff that's already out there, or are we trying to figure out if that's insufficient and something new needs to be created?
Lindley should really answer that, so I'm going to defer it a little bit to him, but I think one of the reasons why we're having this workshop is to consider other alternatives. That's not to say that we are going to stop with the professional or the current existing assets that we have to look and detect and find asteroids and observe those asteroids. But as you know, there's a variety of techniques, there's a variety of different ways of doing things. Even within our own professional community, we have different ways of doing things and detecting asteroids and characterizing them. So I think one of the things about this workshop is that we are looking for those new ideas. We specifically did not have people come in who we're very familiar with. We know their techniques, we know their assets very, very well. We work with them on a constant basis. We're more interested in getting new ideas, opening up the trade space, as you will, and trying to see if there's anything that we can leverage that maybe we haven't had before.
And so perhaps we could throw that question to the audience. This is not a forum in which we should provide the answers. This is a discussion forum. So if anyone would like suggested answers to that, please feel free. We have one here, one here.
Yeah, and we can go back online.
Okay.
Just to jump into that, I would say in the particularly in the partnership participatory engagement, the effort really is to throw this out and get as many ideas that we haven't thought about, and engage in a conversation that says, here's state of the art right now. Can we improve on that? Additionally, are there other ideas that we haven't even considered yet? And can we leverage resources to enable us to accelerate on the state of the art right now? So from my perspective in the Grand Challenge, the goal really is to start to figure out what we don't know and figure out where the trade spaces are to accelerate the work by bringing in people into the conversation that we haven't had yet. So certainly in the Grand Challenge perspective, it is see where we are. We have a sense of where we want to go. Where are the gaps, and are there ways that we can creatively leverage to fill those gaps to achieve our goal? And we can certainly talk some more.
And one down here, please.
Hi, this is Dave Morrison speaking. I think this has been a great session, and the whole idea of using the RFI to get new ideas is great. But I would also say that I often found myself not really understanding what issue individual speakers were directing. There is discovery, and there the bar is very high. We have found more than 10,000 near-Earth asteroids. We're finding them at the rate of several a day. There are a lot of professional astronomers involved. That doesn't mean there's no possibility for new techniques, but the bar is high. And you have to ask these folks with particular ideas if they've done anything to test them or their capability. Second is characterization of orbits, astrometry, tracking, where you already have the object found, you already know at least approximately where it is, and I think there were a lot of interesting ideas presented for that, like Jane Wu's LiDAR. And then finally, there is the physical characterization. And while there were a number of ideas presented, I often find myself wondering what question is proposed to be answered. Just going there and taking a picture is not enough. Several people talked about infrared, and in some cases, I was not clear whether they were talking about reflected solar infrared, which allows you to characterize the makeup of the mineralogy of the surface, or thermal infrared, which allows you to determine size. And so I just wonder how we do the next step. The ideas, many of them were very stimulating, but they left many open questions as to what really is intended and what specifically, what problem each speaker was going to solve.
Go, Chris.
Yes.
Go ahead.
So just to put a bookend on my original comment, I think as NASA may expand and consider a variety of options, to date it's been mostly self-organizing in terms of the professionals who have brought capability to the table and identifying what they think is best to do and how they think they can best contribute with the resources they have. I think as NASA casts a wider net, in addition to prioritizing things that they see as important by providing funding for it, I think there also is a responsibility within the agency to actually create a capability to more directly tell people the specific thing that they believe the new identified capability should be doing. It should be looking in this area of the sky. It should be optimizing this measurement because we're interested in a particular result that leads to NASA's interests and the broader interests of the entire enterprise. And that's something that I think as it from photographic plates and markers to CCD astronomy to some pretty high-tech stuff going on today, there's still a long way to go to be complete and to satisfy the challenge, and I think it's going to require a bigger office at NASA to manage it all.
Thanks for your comments.
Okay.
So I thought we may have a question. We've only got one
Um,
mic runner, so. Are you back, Lindley?
Yeah, I'm back with you now.
Good. Would you like to re-ask your question, Chris? All right, we're done. Carry on.
So I was going to ask a question to Clinton, but first I can answer that question about how many asteroids would come within range of laser radar. That's about 20 or 25 a month.
Thank
within
you.
40 lunar distances, right? And you were saying that the software is fully automatic, but surely there has to be somebody sitting there so that when something is detected, somebody decides whether it's interesting to follow up or not.
So just a moment.
So I guess my question is, what's the level of interaction required?
Sure. So in general, when we operate it today, we are looking for man-made spacecraft. We operate it one of two ways. One is where there is an operator at the controls in our office in Manhattan Beach, and the software has audio and visual cues for any anomalies, whether it's a uncued detection or unusual photometry or whatever it might be. It'll beep. It'll turn an image red. It'll do something to cue you to look. We can also set it up to run autonomously if we wanted to just cue another sensor. So let's say we got an anomalous photometric reading and we don't know why. We could have it autonomously cue another sensor in our network to look at it and get some angle diversity and verify is something really going on, or did we, did cloud fly through if there wasn't an operator there to verify something like that. So it operates in both modes. If we were doing post-processing of historic data, for example, it wouldn't make sense to have an operator necessarily sitting there. It would just pull out all the we have what we would call a detection file. It would just be a printout of all the activities, and it would have some cue in there as these are the interesting lines in the output. You need to go take a look at it, and if you want to go back and relook at the imagery, you could rerun it, and it would load it into the simulated sky at that point in time, so you could get the context of it flying like you were in front of it, but you wouldn't have to be there while it was processing. I hope that answers. Does that?
Yeah. And you guys keep all the raw data that you take?
From our telescopes, yes. We have all the raw.
In front.
I wanted to kind of build on Dr. Morrison's comments. One of the purposes I think that is magnificent about something like this is expanding the level, depth, and breadth of participation beyond the usual players. What happens is, unlike Mars, which is not potentially going to kill us at some moment or produce grand new wealth, which is where Lewicki and I live, this is something that should concern us, and it has a tendency to be turned on and off based on an impact or something like that, or a near miss or something like that. So by creating an ongoing interactive conversation with as wide an audience as possible, and yes, we all may make each other a little bit crazy depending on what our level of knowledge is or understanding, and there's a lot of patience called for in all sectors. But by doing that, what we are going to be doing is, in a sense, creating both the professional army and the citizen army that can be deployed to protect the planet. And that's an incredible thing. And I think if you guys can continue to refine this and don't let this be a blip, let this be the beginning of something that grows and grows, we can move from that archetypal, how many books were about asteroids, start with the number of people looking for asteroids is less than one shift at a McDonald's. That's the cliche. If we can, change that dramatically, I think we can do a lot. And you guys should be commended for that.
I think we've moved beyond that now.
Yeah, we're a little bit.
Oh, three McDonald's.
3 McDonald's. 2 McDonald's. 3 McDonald's. Okay. Any other comments?
Just one more go back about the idea of determining areas of focus. Really, this is, particularly in the Grand Challenge, a first step towards communicating with the community. And we recognize we're communicating with a community that we know to some degree, and we expect to expand more broadly. Inherent in the Grand Challenge side of things is the idea that we're not going to dictate what the requirements need to be and do that on our own, that rather it's a co-creative process. So we're beginning that effort and really look forward to not determining how this should look, but rather do it together, because we're not going to own it ourselves. This is going to be a group effort. And so at this point we are a bit vague. It is grand, but the purpose is to begin the conversation so that we can determine what the requirements are going to be together, so that we can agree on and have that shared understanding that allows us to share that work. So hopefully that clarifies a little bit more, Chris, where we're coming from on that.
I just wanted to say, tomorrow afternoon we'll be discussing this in another session, so we can continue this debate then. Yeah.
Any other questions from inside the room? Discussion? Thought we had one over here. Yeah.
Is there?
So we want to do this one.
We should ask Lindley.
Yeah, Lindley, we want to give you an opportunity to say something if you'd like, if you're still online.
Yeah, I'm still here trying to manage some things for anticipated shutdown, unfortunately. Well, I really appreciate all the presentations today. We got a pretty broad brush of all the different areas, technologies and techniques that can be used for asteroid detection and characterization. It really is a very large area of endeavor, and there's a lot of ways that capabilities and resources can be brought to bear to accomplish it. And so that kind of gets us back to why we're all here, in trying to explore where some more contribution can come to the effort that we've had going for quite a while. I think we saw some good ideas here, some things that need further exploration. I think we saw some things that maybe need a little more thought and a little more experience at what it really takes for asteroid detection and observation characterization to see how they might better apply. As to where we go from here, we're taking this information, and it'll take us a while to digest it all, of course. We'll be putting some thoughts together for the plenary on Wednesday morning as to what we saw and where we think that takes us, and what some of the ideas and concepts might be that we will want to look further into. However, I'd also would say to most of the presenters here, if you're international, the opportunity isn't quite as open to you, but a lot of these ideas that were talked about today are things that could certainly be proposed to the Near Earth Object Observation Program in our next solicitation cycle. So be thinking about that in putting a proposal into NASA for your ideas and concepts and what you propose. I don't think I have anything else further to say at this time. The Pauls and I will get together and talk about what we want to present Wednesday morning to kind of summarize what we saw today. But are there any other questions or issues, or I'll also turn it back to the two Pauls to make any comments they'd like.
Okay. No, I agree. I think this has been a great session. I really appreciate everybody's time and effort, especially the presenters. I think we've got some really good, interesting ideas, and we need to go and look at those. And as Lindley said, we'll gather and get back and present some of our preliminary findings on Wednesday morning. We do have some more questions. We do have another one on online, Lindley, that we'll read out, and then we have a few more comments in the room.
Actually, this
Sure,
is,
we got about 15 minutes more here that we can address things.
Yep.
we have a suggestion online from Mike3cap.sub _sub. A wiki containing all the information currently known about asteroids would be tremendous, and this is a participatory technique that we could use to ensure to engage everyone and continue the discussion. So that's a very good one. There's a second one here.
Let's go to David. We have one more, and then we'll have a couple more on the online.
Lindley, this is partly for you from Dave Morrison, because I think you were out when I spoke before. The question I keep coming to is not, are these good ideas? Many of them are, and they're about hardware and software and approaches. Is in each case, what problem is this going to address or solve?
Well, if you'd address that to me, I think that for each of these techniques that were talked about today, we can see where it could be applied to either detection, orbit determination, or object, physical characterization, parameters of an object. We can stand improvement in all those areas, I think. I don't think we have a lock on any particular area. I agree that the presenters may have been a little vague and uncertain about exactly where they may have fit in, but I think part of that is just them being new to the arena and not having the background that some of the rest of us do.
That's very good. Chris.
So I think this is another question for Lindley. This is Chris Lewicki, and I'll channel my best Don Yeomans and talk about the top 3 priorities in asteroid work. The first one being find them, second one being find them, and the third one being find them before they find us. Essentially the effort that we have put in to detection has been precisely consistent with that. And 3-4 years ago, when Flexible Path rolled out and we, as a nation, wanted to pursue asteroids to send humans to them, it didn't take too long to retreat from that because we didn't have enough targets. And it wasn't quite clear that there was actually a response to try and improve that in a meaningful way. And I see it again here in just the last few months with considering the ARM option, where the idea in part of bringing something back near to the Earth was for the potential opportunity to learn from a resource potential. But here again, we have not put the investment into knowing the types of these things so much as we have. We, of course, can't do that before we find them. So my question with all of that context is, how is it that we can sufficiently raise the priority of physical characterization such that when the opportunity comes up, we have a list of things to pick from? It's something that there are the resources out there to do it. They certainly exist all over the planet. They just haven't really been given this sufficient priority and this purpose to go off and create this data set. And that's something at Planetary Resources I'm interested in how to incentivize that from outside the system so that we have more than just a few things that are spacecraft targets that have characterization like JU3 and RQ36.
Well, my answer to that is that whether you're an existing asset, a resource that could be used, or whether you're a concept that's it could be very valuable to the effort, it all takes funding. Nobody can operate on thin air. The better, the greater the capability, the more backing that it takes. And I sort of agree with you that we're not going to accomplish this by, throwing $20 million at it. It is something that does take a more focused and concerted effort to accomplish. I think with the Asteroid Initiative, what the agency is trying to do is enlist other players, other partners around the world in the effort, so that the agency doesn't have to fund it all. Whether or not that will be a successful way of accomplishing that, we'll have to see.
Okay,
but to find a better part of the population, and particularly those that are, an order of magnitude smaller than what we were attempting before, is it takes resources.
I'd like to make a comment that one can even in the maybe time of this workshop put some numbers around this. if we just take the example of detection through synthetic tracking, laser radar is going to cost millions of dollars for maybe a couple to $3 million for a minimal system. But synthetic tracking, the other part, the detection, a minimal system is a high-speed camera at the back end of a fast telescope. Starting from the 1 meter class telescope, if you can design a optics in the back end it would be in the, on the 10 to 20, depending on what you're doing, the $1,000 class, set of optics in the back end of a big 1 meter telescope. Then the cameras, these cameras that we're talking about, are in the $20,000-$30,000 range. In the end, you really want a lot of étendue, A omega, aperture times solid angle. And so it's not outside the reach of the smaller facilities to do that detection and be sensitive to a large number of asteroids by using the technology. I should just put a plug in that at AstroPH, we just submitted a paper to Astrophysical Journal, but it's right now for free on archive, that describes how basically our approach to doing this, and this is something that can scale to much smaller telescopes on the scale of less than $100,000. It's still not peanuts, but it's much more accessible than millions of dollars.
We've had another Ustream question that is basically along these lines, and I'll quote, the question that hasn't been addressed is scale. How many NEOs per year need to have their orbits, rotation periods, and compositions determined? Discoveries are now 1,000 per year, and soon to be 2,000 per year, soon. But characterization is only about 100 per year. So there's a mismatch going on here. And I would comment that, first of all, we can't fight those statistics. Even so, radar observations are going up, IR observations are going up. So these are the two of the key sources of characterization. IR in particular, if we can boost that with space-based IR, I think that would be a great way to continue the characterization and make a dent in the large numbers here. And we have a question at the back. Comment.
Actually, I was going to make a comment about IR. I'm part of a proposal that is probably sitting on Lindley's desk to use the 2 meter at Kit Peak, proposing for 50% time, and that should give us spectra of, I think it's 1,500 to 2,000 a year. And if anybody wants to chip in for the other 50%, then we can double the rate. And it's very cheap. It'd be like 300 million a year. I'm not going to sell anything else. Thank you.
So there's.
And when you're saying spectra, what type of spectra are you talking about? Wavelength range, just.
Sorry. I can't remember the numbers right now. I can tell you later.
Okay, that's fine. We'll talk later. That's fine.
Yeah.
Okay.
Well, let me address the question a little bit. Although, we're finding 1,000, a couple of thousand of these objects a year, you don't have to characterize everything that is found. We want to characterize those that are of interest. Those that are of interest are, first of all, those that may pose an impact hazard to the Earth, and that's maybe 10 to 15% of that population that have any possibility of impacting the Earth. Most of them are in very benign orbits, and then those that would represent a good target destination for either a robotic or human exploration, which is even a smaller subset of that population. So I'm not too worried that the characterization capability lags quite a bit behind the detection capability, because you simply don't need to characterize every rock and rubble pile out there.
Okay, we have another question in the room.
Okay.
We've talked about space-based IR. What about aircraft-based IR? I know that the Sophia aircraft was based out of Christchurch here about 2 months ago, flying missions over toward Antarctica. So I don't know if there's consideration for using that aircraft quite a bit as far as, for characterizations and detections and such.
Right.
That's a good point.
It's good. Yeah, it's something I think that we look into. The Sophia aircraft is also being utilized by other people as well, and they have other projects. So it's a question of prioritizing and seeing what we can do in terms of sequencing, getting everything together. Yes, again in the top.
Quick question, actually it's a question rather than an answer. For thermal IR, there's a new NeoWise paper out, and I was looking at a plot that showed that below 50 meters, they have very few that they saw even during the cold regime. So the question is, certainly of anything of interest to ARM, we're going to go below 50 meters, probably below 10 meters. And so in that class, does thermal IR have a chance? And I don't actually have the answer to that. I just, the observation that NeoWise didn't even come close to reaching it.
Lindley, do you have a comment, or I can?
Well, first of all, NeoWise is a very limited capability. Was designed even to detect asteroids in the first place. We adapted it to that purpose. It has a relatively small aperture and a very narrow field of regard. So that's why it didn't detect all that many asteroids, and certainly not small ones. But one thing it is valuable for in this looking at targets for ARM is that it can help us narrow the envelope on a particular object, on what its size might be. In other words, if there's an object that we're interested in trying to find out its size, and we determine that it did pass through the NeoWise field of view at one point, based on that orbit, we can determine whether what size it has to be to have been detectable by NeoWise. And if it's not detected by NeoWise, then we know it's smaller than that. So, there are things like that, tricks like that you play when your overall capability is limited.
All right, I think with that, we will call it a wrap. Thank you very, very much for all the input, and we will hopefully see you tomorrow morning. Thank you.